Hello, let's get started. I'm Debbie Liu, Executive Director of eSIG, and I want to welcome everyone to an eSIG webinar. For those of you not familiar with eSIG, we're a membership-based nonprofit organization providing members with objective information, resources, and networking opportunities in support of clean energy and energy systems integration decisions. And we do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and we produce technical resource materials. For those of you who are members, thank you for your support. It makes these webinars and other work possible. And for those of you who don't know, we'll be having our fall workshop in Philadelphia, October 27th to 30th, where we're going to talk about large loads, grid forming inverters, and AI applications. Workshops and webinars are open to everyone. Feel free to register on our website at esig.energy or find us on LinkedIn, YouTube, Facebook, and X. So a few logistical matters. All participant lines are going to be muted for the duration of the webinar to avoid unnecessary distractions. And for questions and answers, we ask that you go to slido.com and enter ESIG15 as the event code. Instructions are here. You will see a thumbs up button next to questions, and you can cast a vote to help prioritize the questions that are submitted. And we'll save 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted, and we'll plan to provide short responses to unanswered questions after the webinar. So don't be afraid to ask your questions. So today, we're going to hear from the International Energy Agency, IEA, WIND Task 25/63, which covers design and operation of energy systems with large amounts of variable generation. So this IEA task produced a recommended practices report that discusses power system impact studies with high levels of wind and solar. And today's webinar will compare the recommended practices with modeling practices applied in a study of electrification of the transport and industry sectors in Sweden. And I've been personally super lucky to get to work with this IEA task for the last 20 years. It's been a fantastic group of international researchers that share methodologies and results from power system studies. It spans economic analyses to sector coupling to transmission and reliability studies. So today's speakers are Professor Hannele Holttinen, who is the operating agent for this IEA task, and also the GPST Pillar 5 lead, and also a professor of practice at Aalto University. She will be joined by Professor Lisa Göransson and Professor Pei-Yuan Chen from Chalmers University of Technology in Sweden, who will discuss the transportation and industry electrification case study in Sweden. And finally, rounding out the panelists is Professor Damian Flynn at the University College Dublin in Ireland. He focuses on power system dynamics, grid integration of renewables, and power generation control, and leads the stability work under the IEA task. Just a short reminder again, use slido.com with an event code at ESIG15 to ask your questions. And now I'm going to turn it over to Hannele.
Thank you, Debbie. So indeed, we are trying to make this presentation as a dialogue between Damian and me from the task force that have been writing this edition 3 of the recommended practices, and between Lisa and Pei-Yuan from Chalmers going through the work in Sweden. So the next slide just shows you our 2 reports that we are going through today, the recommended practices and the Chalmers study on electrification in Sweden. And in these recommendations, we have these checklists of recommended practices, and we are now comparing how an example case study has been following these recommended practices. So the next slide shows you the context of the recommended practices. So we have made this big report about data and methodologies to recommend. We have made it in following a flow chart. So first you make your future power and energy system design or scenarios that you want to study. and then you will check the feasibility on the operation of the system, on the resource adequacy of the system, and on the dynamics. And these checklists, as we are showing today, can also be used as a benchmark to any existing study. And also, this report is only about how to perform studies. We have the checklist, and we have a lot of text describing the issues and challenges, but there are no results in this report. For that, we have other reports in our task website. So next, I would like to hear something about the studies. I hand over to you, Lisa.
Thank you, Hannele. So just to give you a context of why we wanted to carry out this study in Sweden. So in Sweden, we are facing a doubling of the electricity demand, mainly due to electrification of transport and industry. And we have very good conditions for wind generation across the country, but there were concerns expressed as to the total cost of a wind-dominated power system. And the government then proposed financing of new nuclear power. So in order to support decision makers, we just wanted to do the calculations. What would the cost for society be to meet this demand with a wind-dominated system or in a system where we also had financing of new nuclear power? In this graph, it gives you an overview of the modeling methodology that we applied in the Swedish case study. So at the heart, you have three different models. There are two capacity expansion models, and both of them, they minimize cost to meet the demand for electricity, heat, and hydrogen for society. They both have relatively high temporal resolution, but in other parts, they are very different. So the leftmost capacity expansion model has a coverage of the full European continent and also every 5th year from now until 2065. We run that model first and use electricity prices between continental Europe and the Nordic countries in order to then move over to a smaller geographical scope. So our second capacity expansion model has a geographical scope of the Nordic countries, but very high geographical resolution, representing 400 nodes, more or less each transformer station in the high voltage transmission grid. And this capacity expansion model, it was designed in order to collaborate with our power flow simulation model to the right. So our power flow simulation model, it takes the generation and the loads from our capacity expansion model of the Nordics, and then it runs full power flow with active and reactive power to check the feasibility of the system from a physical perspective. In addition to these three models at the heart of the modeling methodology, we also do two different post-analysis to complement them. One where we look into the need for investments to manage interannual variability, and one where we look at need for additional investments to manage intra-hourly variability. So Hannele, how does this approach compare to the recommended practices?
Well, this is actually a bit different than what we were foreseeing, which makes it very interesting to see how you do with our checklists. So this is a list of the checklists that we have in the report, and you can see in a sort of grayer color some of the checklists that were not relevant and used in this study. So the capacity value of wind and solar was not assessed, and the distribution grid was not studied. But otherwise, we will now go through all these lists, and generally just to say that indeed not all studies will cover all of these. We can say generally that when you have more and more wind and solar, it is recommended to study all and check all these aspects. But especially when you start with first studies for lower shares of wind and solar, only part of these is really necessary. Okay, so let's start with power and energy system scenarios. So how did you do them?
Well, in short, in the Swedish study, what we did is that we had these two capacity expansion models, both with a high temporal resolution, but then one with this long time span and one with a high geographical resolution. And with both of these, we compared two different cases. One case where in the Swedish system we didn't have new nuclear power, and one where we did introduce or force in new nuclear power. And the approach was based on the assumption that the variability and grid limitations have a large impact on total system composition. So it was based on this that we designed this setup. So these figures show example output of our kind of large-scale capacity expansion model. On the top, you have production per year in terawatt hours in the Swedish system, and on the bottom, you have storage capacity. So if we look at the production, the two leftmost graphs, they illustrate systems where they're very similar. Here we basically minimize cost for society to meet the demand. And in the rightmost graph on the production, we then enforce new nuclear power capacity, 3 gigawatts by 2040 and another 3 gigawatts by 2050. And as you can see in the Swedish system, we already have a system which is based on low CO2 generation. So we have existing hydropower in dark blue in the bottom in all the graphs. And then we also have existing nuclear power in red in both or all three of the graphs. And then when we have this electrification primarily of industry, it increases the load dramatically in the system up until around 2035. And we can see that a large part of this new load coming in is by what is light blue in these bars, that is onshore wind power. And we can see that onshore wind power is basically doubling compared to today in all the three different cases up until 2035 to meet this new load that is coming in. If we then have new nuclear power coming onto the system, we see that it mainly replaces onshore wind and offshore wind in Sweden, and it has low impact on the import and export balance. And in all the three different cases, we have a situation where we have more than half of the electricity demand met by wind and solar power by 2035. So when we have this much wind and solar in the system, of course, it can also be cost efficient with storage. So in the bottom, you see investments which are cost efficient according to calculations in terms of storages. So we have hydrogen storage and heat storage in these systems. The electrolyzer that are used for hydrogen production, we want to oversize them and be able to back them off from electricity consumption and then have storages that meet that demand during that time period. And here it's found that it's cost efficient to do that and have storages which can meet the hydrogen demand for 3 to 4 days. We can also see that when we have large-scale heat pumps, which meet the demand for heat in district heating systems, we also want to accompany these with large-scale heat storages, such that we can avoid heat pump operation in the range of 1 to 2 days. And if we have then new nuclear capacity coming into the system, we have a little less of storage investments. And then if we look at the results from our other capacity expansion model with high geographical resolution, we can instead see the placement of these generation capacities across the Nordic system. Overall, we get very similar total system composition with our kind of large scale, rougher capacity expansion model, our detailed capacity expansion model. One difference that we see is that we get less solar PV investments with our high geographical resolution, because PV production is concentrated a few hours of the day, and then it becomes, we need a lot of capacity basically to transport it from one node to another. We can also see that in these calculations, we have assumed that the transmission grid is what it is, and in terms of capacity, but we've also included planned reinforcements up until 2040, but we do not allow for new transmission grid investments. Still, we see that it's possible to meet this large new load coming in with new generation capacity if it's placed in a way that is convenient for the transmission grid. That means that we have a lot of new generation placed close to locations where we have a lot of industrial load coming in. That means southwestern part of Sweden, but also the northmost part of Sweden. So here we can see we have on the top the placement of onshore wind, which is typically then focused on the southwestern part and northmost part. We also see that we have offshore wind in the southwest and also solar power in the southwest to meet these new loads coming onto the system. And in a case where we have new nuclear power capacity, it is mainly renewables in the southern part of Sweden, which is replaced by the nuclear power. So Hannele, how did we do?
Okay, so first of all, our first recommendation is that when you have a lot of wind and solar in your future system, you should use a capacity expansion model to optimize, and this you did. And then when using these capacity expansion models, so what should they include? The recommendations are seen here. So first of all, you should have demand flexibility, storage, and sector coupling in your future power system and energy system. And yes, this one, I think you did well. Yes, that's right. The other recommendation is that when you have a lot of wind and solar, you should somehow have the short-term balancing represented in your capacity expansion model. And have somehow the uncertainty there. And how did you do that?
So we don't include uncertainty in the capacity expansion modeling. We do have a relatively high temporal resolution in both the models in order to capture kind of the short-term dynamics and needs for flexibility. But when it comes to variations within the hour, then we do this post-analysis instead.
That's right. And then going forward, the grid limitations and stability constraints become more important when you have these really high shares of wind and solar. So as you showed, it really had an impact. So how would you rate this one, Lisa?
Yeah, so I think with the grid limitations, that was one of the main purposes for having this high resolution capacity expansion model and actually do that extra step. And I think that's important when we see from the Swedish perspective that we have large loads and generation coming in while we don't see the same type of build out planned for the transmission grid. So the grid will likely have a large impact on this placement of new generation. When it comes to stability constraints in these capacity expansion models, again, this is something that we're doing in subsequent work and subsequent steps, but they're not included in these first initial steps to design the scenarios.
Okay. And then also, in many cases, the operational practices need to be reconsidered for future system needs and services. How did you do that?
I mean, we do account for new ways of operating these systems in terms of, I guess, then including flexibility, different ways of using loads that we haven't used, that we aren't used to today. Today, I mean, most of the variations are managed by supply side in terms of hydropower. But then again, more detailed TSO and stability considerations where we also need changes in kind of how the TSO is actually setting standards for how the grid should be operated. That is also something coming in and being addressed in the future steps or other steps that we're going to hear about later.
Indeed. So a nice green check here. All right, let's go forward to the next part. Here we have resource adequacy estimates. So how did you do that?
Yeah, so for the Swedish study, what we did was that we did a post-analysis to look at the net load for 40 weather years to assess what was needed in terms of, we're making sure that we can meet the demand basically all hours and also during extreme events. And the reason why we had this setup was that we have done previous work within the research group where we've looked at extreme events and many weather years in capacity expansion models and have seen that these extreme events have relatively low impact on total system composition of the systems, but indeed there is a need for additional investments and then primarily in gas turbine capacity and fuel storage. Reason being simply that this is something that happens very seldom, so we need to deal with it with something that has a low investment cost. And because we've had these results from work in the past, we figured it was sufficient to do a post-analysis and not couple this immediately into our capacity expansion models. So the way that we did it was that we mapped out the net load using the capacity of wind and solar that we got from our capacity expansion models, but then using that to calculate the net load. That means the demand for electricity reduced by the wind and solar power production using data for 40 different weather years. And we're mapping this, as you can see, in terms of amplitude, duration, and recurrence. So here we have the amplitude of the net load on the x-axis. So when that's positive, that means that we need more generation or more power into the system to meet the net load. And on the y-axis, we have the duration. So for how long do we need more power? That basically reflects the size of our storage needs. And then the coloring here shows how often this happens. And by knowing how often it happens, we can decide on how we want to prioritize between investment cost and running cost. So if something happens very seldom, then we want something with really low investment cost. So if we look at the kind of bottom of the graph, where we look at the highest amplitudes, but the shortest durations, at that peak we can see kind of what is the peak capacity that is needed in these systems. And when we did that analysis, we found that we need an additional 3 gigawatts of peak power compared to the calculations from our capacity expansion models. And this could either be supplied from the demand side using individual heat pumps to control these. We have around 5 gigawatts of individual heat pumps in Sweden, or by additional gas turbine investments. But we can also see that we have a contour where the need for power is reduced with the duration, but along this contour, it's not completely clear, it's not obvious which is the most challenging event, but the whole contour kind of defines the most challenging events. And we, for example, can see that at 3 days of duration, that means 72 hours on the y-axis, we have a need for relatively high power still. And if we compare this to the needs that we had in the capacity expansion model, we saw that we needed another 2 gigawatts of capacity with 3 days of duration. And if we still have our existing hydropower and our existing nuclear power in the system, they can meet these total needs as well. But if we phase out the existing nuclear, we will need to complement the hydropowered gas turbine capacity. So let's go to the checklist, Hannele.
Okay. So first thing that we have found really important to include are the neighboring areas.
Yes, so in all this analysis, we do include the possibility to trade. And that's also the reason why we want to have this kind of rougher, large capacity expansion model as well.
Yeah, that was good. And then the interannual resource variability is the second very important thing.
Yes, exactly. So this is what we capture by looking at 40 different weather years. So here we really try to look into all the different types of variations that we can see in the historical data in terms of the net load.
That's right, and there is a recommendation also to include future-looking climate change impact in the data used in these long time series. Now, this recommendation actually comes with a footnote. This is an emerging thing happening, so we cannot yet be very sure that these time series are as good representing the wind and solar correlations and variability as the current very good data we have, the long historical data. So that's why this is a not so strict recommendation already by reading our checklists. So no worries if it's not yet taken into account, but it's just a reminder that this is an important thing for future.
Yeah, and in other work, we looked at the impact of climate change on wind power in the Nordic countries. And we saw low impact on both the variability and the resource availability in the Nordic countries for wind. So we feel relatively comfortable, even though we did use historic data here.
Great. And one thing that is very important for future studies is really look at the flexibility options, also covering resource adequacy needs.
Yes, definitely. And these were included in all the analysis. Yeah. Shall we move on?
Yes. So the next slide. is showing a couple of additional things to use. Yeah, so what we recommend is to take a more detailed look using several metrics, several criteria.
Yes, exactly. And in this case, we wanted to see the full cost of a system with and without new nuclear power. So we didn't want to estimate the loss of load and get different risks or different loss of load for two different systems. But we wanted to make sure we could always meet the load in both cases. So that's why we took a slightly different approach here. But we did use this kind of mapping of the net load to show both the amplitude, but also the duration and how often things occur. So in order to get kind of a good coverage of the full understanding of this.
Yes, indeed. And then the next point is actually a bit repetitive. It's for the load projections. We already saw that you really are looking and including new electrification loads with flexibility, and the climate change impact again here is a bit more challenging to take into account. So maybe that's like okay to be yellow here. And then for the last point, it's also something that should you have problems in your meeting your reliability targets, there's also the recommendation to actually check what relaxing these targets would mean.
Yes, but here there was no need to do that because we just added capacity until we met the load.
Yes, that's right. Okay, then the next part.
We're handing over to Damian and Pian.
Damian, that's right.
Yeah. Hello, everyone. So we haven't really talked too much about location yet. So next we're going to look at transmission network under, first of all, steady state conditions. So Pian, can you tell us a little bit about what you did here?
Yes. So from here, we from the capacity expansion model for the Nordic 400 node system, that we have the dispatch. However, the expansion model is based on a so-called DC power flow, which means that it respects the thermal limits of the transmission network, however, does not evaluate the voltage or the radial power compensation in such a model. So here is the idea is to evaluate if these dispatch scenarios are also respecting the reactive power and voltage requirements in the transmission system. So in the next slide, what we have calculated here is that, I mean, before we do a disturbance analysis, we want to see how is the reactive power flow in the system. However, we don't really know at each bus how many shunts are available in the system. So what we did here is, instead to turn the question around, if we want to maintain the system voltage at 1 per unit at all buses, how much shunts do we need? And this is what we have, the results that we have obtained. The blue bars on the left side is how much shunt capacitor banks that we need. And we have calculated this per bus, but we have aggregated this at the bidding zone level in the Nordic countries to show the results. Whereas the orange bar on the right-hand side reflects the shunt reactors that is used to, for example, handle Ferranti effect when we have over voltages. And we have the historical case, which is for 2022 scenario, and also for the 2050 scenarios, where we have 3 cases, as Lisa mentioned before. What we can see here is that, for example, when we take a close look at the Finland on the most right-hand side of the figure, that we can see a significant increase in both the shunt capacitor banks and the shunt reactors, and in all the 3 future scenarios. And these are primarily due to the increased electrification, thus the load increase in the system, as well as the increase of the renewable generations, especially the wind parks. So this is what we have done so far for the current for N-0 case. And the next step is that we are going to look into contingency events with n-1, and where we will evaluate how much dynamic reactive power that is needed in system, or if we have sufficient dynamic reactive power, for example, from the synchronous generators and the power park modules, to keep the system voltage within acceptable range after a n-1 contingency.
Okay, so perhaps we could jump to the next slide just to see how you compare against the recommended practices. So I think beginning with the power flow cases, can you just briefly talk about how you've selected the cases?
Yeah, so here we actually run for all the hours over a year in the power flow using AC power flow. So yeah, that's what we did.
Okay, and can you tell us a little bit about how you assess the congestion in the network? I think you talked about DC power flow earlier.
Yes. So before, in the dispatch scenario, it's based on DC power flow, so which is only the film assumes that there's no reactive power flow in the system, and we only focus on the active power flow. And there we also only evaluate the thermal limits. And then now in this model, we also incorporate to evaluate the dispatch scenarios obtained for DC power flow, but in an AC power flow to check if they are AC feasible.
Okay, and Lisa mentioned earlier that you're looking at a target of 50% average VRE and maybe 75% instantaneous VRE. So have you thought about grid strength and short circuit levels and things like that?
Yes, absolutely. However, we have not yet started this work, so this will be our next work in line after we did this n-1 analysis for the dynamic reactive power requirements.
I think we'll be looking at the operational impacts. So we're looking at sort of hourly to daily and perhaps sub-hourly as well. So Lisa, can you tell us here what you did?
Yeah, great. So in the Swedish study, what we did was that we focused on having a high temporal resolution and multiple flexibility options already in the capacity expansion models. But we didn't do any separate or individual unit commitment dispatch modeling in this work. And this was prioritized because under the underlying assumption that the impact of variability on investments has a larger impact on future systems and future system costs than the impact of uncertainty on operation. However, this remains to be tested. This is basically based on kind of, well, experience from running a lot of these type of models. Then we also do a post-analysis of variations within the hour to cover that part of the aspect. And the reason why we do that as a post-analysis, that's basically based on previous work where we looked at variations and uncertainty within the hour. And if we add static requirements on that in a capacity expansion model, we saw that the most impact we had was that we get investments in stationary batteries on top of an already defined system composition. So then we felt pretty comfortable with doing that as a post-analysis.
Okay, sounds good.
And then I promised I didn't have animations, but realize now that I do. So this graph doesn't come out as it was planned. But it was mainly to persuade Hannele and Damian that we actually do look into kind of detailed hour-to-hour operation and always meeting the net load in our capacity expansion models. So what it is an extract from the capacity expansion models, where we start with kind of what is the demand of the system, what is the net load of the system, and then we add one generation unit, one flexibility measure at a time to gradually see how we meet the net load every hour. And in the Swedish system, the main contributors are, well, to some extent we have trade as a contributor that deals with the real peaks in the net load, because if you trade with your neighbors, those extreme events don't happen at the same time over a large geographical scope. Then we have hydropower in Sweden, and that's obviously a blessing. So that deals with a lot of the positive net load variations in the Swedish system. And then we have the flexibility from electrolyzers and heat pumps in the district heating system, which avoid using electricity during low wind events. And by that, we can meet the net load every hour in the Swedish system. So I can say that there is a combination of different flexibility measures that work together. And in the Swedish system, we have this both hydro, the hydrogen flexibility, and the heat pump flexibility, which all operate on this kind of a little bit longer time scales, which match really well with the wind variations.
Okay, thank you.
And if we then look at the, I also want to look at the variations within the hour, just because we did this statistical analysis so briefly. What we did is that we looked at the ramps of wind and solar from 1 hour to the next. And we could look at how large are those ramps. And then in the worst of cases, we need to deal with the full extent of these ramps by something outside of our kind of scope or system that deals with the hour-to-hour variations. And we can see here just the size of these ramps when we do the calculations. We have the largest ramps from solar PV, even though they are a smaller contributor in terms of energy supply to the system. We can also see that if we look at the total need to match these ramps, that's much smaller than the addition of wind and solar together. So both wind and solar ramps don't happen at the same time. And here we also count them for the possibility to use curtailed wind and solar to deal with some of these issues. And then we get a total need for stationary batteries to deal with the inter-hourly variations. Still, it's a substantial need for stationary batteries. 9 gigawatts in the case with new nuclear and 12 gigawatts in the case without new nuclear power. But that's a kind of summary of what we did in terms of operations. So Damian, what do you think of this?
Sounds good. So briefly, can you just tell us a little bit about how you can consider your wind and PV time series and your load time series and the coincidence between them?
So of course we took care to take all of these time series from the same historical years so that they all represented the same type of weather. So in the large capacity expansion model covering the large geographical scope, we used 2 weather years, 1991 and 1992, because they are subsequent from each other, but one is a wet year and one is a dry year. So having a lot of hydropower in the system, we figured it was important to do the combination. And then in the eHub model, with all the 400 nodes, we couldn't afford to do 2 weather years. So here we chose 2019, which is normal from kind of hydrological and also wind perspective, well, as normal as you can be.
Okay, and when you've got large shares of wind and solar in your power system, you begin to think about things such as stochastic optimization and rolling planning. So is that something that you saw a need for and introduced?
Yeah, since we did all of the kind of operational aspects in our capacity expansion models, we couldn't do rolling planning horizon. That wouldn't work out with the maths of the problem. Then we need to look at the full problem at the same time. So to do that, we would have needed a separate step with a unit commitment model. We didn't do that in the Swedish case study, but it's definitely worth discussing whether that should be like an addition to our 3 models, a separate unit commitment model with rolling planning horizon.
Okay, and how did you define your reserve targets? Did you think about the uncertainty associated with wind and solar and also the load as well?
Yeah, so we did the analysis of ramps to kind of cover a bit the needs to cover uncertainty and variability for within the hour. But again, we didn't have forecast error and those kind of things included in that analysis. And we have ongoing discussions with DTU, who are developing a method on that we hope we can add to our modeling package and do this a little bit better.
Okay, so we jump to our next slide. Okay, so very importantly with high shares of renewables is thinking about flexibility sources. So how did you think about that?
Yeah, so we simplified thermal cycling in this work. In other works, we've done it more in detail, but in this work, we simplified it, but we do include minimum load level for nuclear power in the systems. We do account for all the trade and possibilities to work together with the neighboring systems, but also their limitations as we co-optimize the full European continent in one of the models. And then we do also include this sector coupling with flexibility from heating and flexibility from hydrogen production with electrolyzers. So here we have a relatively good coverage of different flexibility options.
Okay, well, that's good. You've sort of answered my next question. So maybe I'll just go to my final question here, which is, how did you assess the flexibility needs of your system? How did you assess whether the various things that you were considering were good decisions?
Yeah, well, so since we do this in the capacity expansion modeling step, we don't have the problem that you may have in unit commitment or if you add storages in the dispatch step to see if whether they are actually cost competitive or whether they could actually cover their cost. So since this is part of the kind of investment optimization and part of the balancing between how much wind and solar you get into your system relative to how much gas turbines you get into your system and how much storage you get into the system, costs will always be covered and they are always feasible from an economic perspective in that sense.
Okay, sounds good. And then our final page of operational impacts. So the transmission system, how was that considered?
Yeah, so the transmission system, because we have this Nordic 400 nodes model, we do account for limitations in the transmission grid at a relatively detailed level already when we take investments in generation and storage. So here we can see kind of if we need storage in addition, because we have, for example, transmission limitations.
Okay, so I think our next topic is stability and incorporating that. But briefly, how did you consider stability in an operational timeframe?
Yeah, so the only part of stability was the post-analysis where we looked at the need for stationary batteries to cover, let's say, frequency control in the system. And then we do have already a large share of hydropower in these systems, and this hydropower has a minimum operational level means that there is always some type of or some amount of rotating mass in this system as a basis. So on top of that, we then added the possibility to fast feed in of active power using stationary batteries.
Okay, thank you. So I think we'll now move on to our final technical topic, which is really dynamics or the stability aspects. And I think, Ewan, you can tell us a little bit about what you did here.
Yes. I'm afraid that we have only started the work on the dynamic aspects, so there will be a lot of red crosses later when it comes to that. But we have often got the question on, from these dispatch scenarios, like, are these dispatch scenarios, are they robust enough in real-time operation? So this is where we really want to address such questions in this study. And then the first thing we will look at it is the frequency and the voltage dynamics. In the next slide. In the Nordic system, we are a little bit also lucky in the sense that for the traditional synchronous machines, we don't really have a rock-off protection. And for the wind farms, we also have a relatively relaxed rock-off protection where the system maximum allowed system rock-off is 2 Hertz per second. So in this sense that we do not really need a huge amount of rotational energy in the system to be able to limit the rock-off to 2 Hertz per second. And considering also that we have so much hydro in the system, and then also the existing nuclear will also remain to 2050 scenario. So we are pretty safe in terms of rock-off requirements. And then in the next slide, where we will show a bit of the what we have in order to be able to capture the frequency dynamics, and based on this power flow model that we have developed, the first step we trying to sort of model is to check that do we have a right amount of kinetic rotational energy from the synchronous machines in our model as compared to the actual measurements done by the Nordic transmission system operators. So here we have done an hourly calculation of the rotational energy in our model, which is shown in the blue dots, whereas the actual measurements from the Nordic TSO are shown in the orange dots, which is a little bit of the shorter, smaller variations. Overall, I think we capture it pretty well in our model. And you can see that in the summer period, a lot of lower rotational energy, which is also usually a concern with the larger disturbance during a summer night, for example, when the system have a lower rotational energy. And comparing with the measurements, our model tends to underestimate the system kinetic energy when the kinetic energy is low, so which is relatively a safe, it's a conservative estimation, which is positive from our side, so to speak. And then the next step, Then the next step is trying to capture, for example, such a frequency event. And the frequency nadir is one important measure for us to capture in such a model, because it is what is used for if the frequency go below a certain value, we will start load shedding in the system. So that is something we wanted to avoid. And so this is important for our dynamic model to be able also to capture the frequency nadir, which is primarily determined by the size of the disturbance, the system inertia, or the rotational energy, as we shown in the previous slide, the volume, and then the speed of frequency containment process, which is also called primary frequency control in the, for example, in the American literature. And then also the load frequency and the voltage dependence. And in this particular case, we do not, in this particular events, we do not have the fast frequency reserve, the FFR. Otherwise, it will also impact the frequency and nadir when the FFR is activated in the system. So that's what we have become so far at the moment.
Okay, so let's look at the recommendations. Always with stability analysis is working out which snapshots you should actually look at. So how did you decide what cases to look at?
From the dispatch scenarios, we have like a few thousand of hours over a year. And also for each hour, we have so many contingencies events to look at it if we wanted to go through every single component in the system. So this is very difficult to do a dynamic study for each of these scenario. So what we have been thinking at the moment is that so the traditional high load and low load scenarios we will need to cover, and also high IBR shares like high wind farm and HVDC and converters, other converter-based generations. So these are important to consider. And also we will also look at since Sweden and all the whole Nordic system is such a long country as well. So we will look at the very high north to south flows, and then also the opposite high south to north flows, and then also east to west from Finland to Norway, and then also Norway to Finland. So we were trying to look at these scenarios to filter out the scenarios for analysis.
Okay, so next on the slide we have frequency stability and voltage stability. And I guess what I'm wondering is, obviously synchronous generators can help you here. Have you also thought about your wind and solar as being able to help you with frequency and voltage stability?
Absolutely. Currently, in the current grid code, there are no specific requirements, especially when it comes to frequency stability and with the voltage stability, the requirements, the grid code requirements has been sort of gradually updating it so that they are providing also a certain amount of reactive power dynamically as well. And this is absolutely we are going to consider in our study.
Okay, that's good to hear. So if we go to the second slide. So I think you said earlier we might see a few red X's, and
Yes.
lo and behold,
Yes.
we have a few red X's. So
Yeah.
perhaps we could talk a little bit about, stability takes many different forms. What forms of stability or what issues are you particularly concerned about, and hence that you might focus on first?
I think the trend from the transient stability point of view, which is also very coupled to aspects, is that here we would like to also see that the different control mode of the wind and the solar in the system to support the grid, the rated power and the voltage. And also there will be new requirements coming out on the demand on the reactive current injection during fault. So this is something we will definitely start with. And then also the next step is also that.
So if we can move on to our.
Sorry?
If you continue talking, that would be good.
All right. Yes. And then the next step is also that both Sweden and Finland has a lot of serious compensation lines, since it's we have a long distance transmission. So it makes it really relevant to study the resonance stability in that aspect.
Yes.
And we also
yes,
do
I would
still
agree.
have a lot of type 3 wind farms as well.
Okay, and then our final dynamics slide. So you've alluded to the converter-driven stability issues, but also common mode events as well, where something happens that affects, a wide area due to a common event. Is that something that you've thought about?
Yes, converter-driven stability has becoming really a center of discussion in the Nordic system, and there has been also grid code requirements coming out of how, for example, wind parks should test so that it fulfills the stability requirements in the frequency domain, for example. And so that will be definitely a follow-up study from after our previous after we checked the previous red crosses. And then the common mode fault, actually, it is very interesting that that is mentioned in this checklist, because we actually have another project that is ongoing, look exactly the same features here that go beyond a little bit of traditional N-1 as a contingency events, but also like N-1-X, such as, for example, if you have a fault in the transmission system where the fault propagates also to the distribution system. And we have a lot of, for example, residential solar PV connected to a low voltage grid. And these are, usually there are not very strict grid code requirements on them as compared to the large generators connected to the transmission system. And so it's extremely important for us to look over the protection of these generators, small generators in the low voltage grid, so that a voice deep in transmission system does not cause cascaded tripping of these small generators of a larger scale over a larger geographical area, which will in turn impact the system frequency. So
Okay.
this is also an ongoing study.
Thank you very much, Pei-Yuan. It sounds as if you've got very many interesting challenges ahead. So I will now hand you back to Hannele.
Thank you.
Thank you. And I see that we are ending our webinar timing, so we'll go a bit more briefly through the analyzing and presenting results. So Lisa, you just wanted to say a couple of words on the summary slide. Next slide.
Yeah, I just want to say 2 words on kind of what came out of this whole work that we did. So what we found in the end was that in the system, which was wind dominated, we needed indeed more storage, we needed more stationary batteries, more gas turbines. And it's of course super high importance to map these needs and create incentives, regulations to put them in place. But what we could also see was that the cost of these components is significantly smaller than the additional cost of new nuclear power for the Swedish system. So if you see the table to the right, this is where we just go through the cost of all the different components and also the needs of these components to cover the different aspects to meet the needs of the Swedish power system.
Indeed, this was a very interesting comparison study, and also looking at the recommendations. What was really nice that you were really comparing full scenarios, which has been found one of the stumbling blocks of trying to capture impacts of wind and solar. So that was very nice to see. And then we have general recommendations on how to present the results. And also we hope that to list the main assumptions and limitations, our benchmarking exercise is useful for any studies that you are making. So going forward, I would just like to hear some views that you have, Lisa, about this process. How was it using the recommended practices as a checklist of the study that you already did?
Yeah, I think it was very useful to us to really get to go through and discuss these different aspects. Maybe it made us reflect a lot on kind of our ways of working and what we need to do to complement the work that we're doing and how we prioritize in the future. Some experiences that I bring with me is, first of all, I mean, collaboration is required to carry out these full integration studies. One of the first things that I did to start developing this work was to knock on Pian's door. So I'm an energy system analyst, he's an electric power engineer. We're needed both for cost efficiency and for reliability. So we cannot do this without one another, so to say. The other thing we realized is that you need a lot of different modules in order to cover kind of all of these different aspects, lots of modules, lots of models to cover them all. And I think here it's important that we help each other out in the modeling community as well, that we have tools that we can share between each other, maybe some modules that can be shared between to be coupled to different capacity expansion models and unit commitment models that can analyze different aspects. So because it's important not to make it too difficult for smaller research groups to also be able to do high quality integration studies. So for this, there is a need for kind of a collaboration across the modeling community as well. Then I think it would be super important to investigate the consequences of missing out on some of the steps, on simplifying some of the steps, both so we can help to prioritize between kind of how we focus when we develop our modeling frameworks, but also to better understand and interpret results if some of the components are not there. So these are some of the learnings that I take with me from having done this together with you.
Great. And I would just like to end our presentation by reminding that this is really work in progress. The energy systems are evolving, and the methods and the tools are evolving, and the data as well. So we have a lot of new opportunities and challenges ahead of us, also taking into account a lot of things that are happening with the load transition and not just energy system transition. And finally, the last slide is just to thank you and give the link to the recommended practices. And we do have a paper from the Wind and Solar Integration Week last week that we will also put up in the IEA Wind Task 25 webpage very soon. Thank you.
So I wanted to thank you all. That was a really nice way to illustrate the various detailed recommendations in the recommended practices report, looking at data, assumptions, and modeling what's needed to undertake a good study. we have some questions on Slido. I realize we're going to hit the top of the hour soon here. If you're okay staying on for a little bit here, maybe we can talk through some of the questions. So the first question is from John Simonelli, and he asks, system stability was evaluated. Did the high wind IBR scenario consider short circuit strength issues?
Yes, we will. It was not probably clearly mentioned. The shots, like low electrical strength, like a low short circuit strength, will be considered in our analysis.
Great, thanks. And Vindra Kanai asks, what LOLH, loss of load hours, and LOLE, loss of load expectation, indexes were used? How stringent were you with those numbers?
So in this work, in the Swedish case study, we didn't use those to evaluate resource adequacy. Instead, it was important for us to try to assess kind of what is needed in terms of investments in order to make sure that we meet the needs all hours. And then we had these 40 weather years. Obviously, things can happen if you look at 100 weather years, which doesn't cover those 40. So, but we didn't calculate the indexes. Instead, we looked at the 40 weather years. We looked at all investments that are needed to be added to meet all of those hours, in order to be able to say that both of these systems can kind of meet, in principle, all events.
Great, thanks. And Vindra Kanai has another question. Can you speak to how you merged the capacity expansion model of only a few years with the weather models of 40 years?
Yeah, so we took the investments in wind and solar power from the capacity expansion models, and then we took load data, wind and solar data for the 40 weather years, and then we calculated the net load for all of those 40 weather years, and then we mapped the net load and did the post-analysis calculations based on that mapping. So that was how we used the capacity expansion model results, but then over to the 40 weather years.
Great, thanks. And John Simonelli asks, in the offline stability testing, were generic or detailed wind models used? Any plans for EMT testing? Will there be real-time stability testing in operations?
The plan is to implement for example, the wind models as generic, for example, as WAC models. That's our plan. And the EMT testing, yeah, some of we will try to sort of filter some of the critical scenarios, for example, from RMS simulation, and then we will carry them out on the more detailed EMT studies as well.
Okay, great, thanks. Maybe we'll just take one more here and then we'll wrap it up. Let's see. Someone asks, how did you project and how did you project and account for wind and solar variability in the capacity expansion and in the power flow?
So we had a relatively high time resolution in the capacity expansion models. So in our large scope capacity expansion model, we used these chronological clustering to select on average every third hour of the year to be included. But since we used the chronological clustering in the selection, sometimes it was just one individual hour in a cluster, and sometimes it was a little bit more than 3. And that was to be better in kind of also capturing more extreme situations. So that was the way we captured kind of variability in the large scope. And in the 400 nodes model, we used every third time step, so 3-hour time resolution.
Okay, great, thanks. So I want to thank you again, Hannele, Lisa, Peyo, and Damian, for your presentation today. As I mentioned earlier, an email is going to go out once the video file's been posted. We'll answer the few questions we didn't get to, get them posted as well. And I just wanted to thank all the participants for their engagement. And we look forward to seeing you again soon. We have a webinar tomorrow on wide area resource adequacy assessments. We have a GPST ESIG joint webinar on Monday on modular control center systems. And we have a webinar on Wednesday on flexible solar interconnections. And I apologize that we seem to have gotten all these bunched up. Go to esig.energy under events to get more information. But Hannele, Lisa, Peiwan, Damian, thank you so much for this very timely, informative webinar. Thank everyone of the participants for their interest and look forward to seeing you again.
Thanks for having us.
All.
Thank you all.
Thank you.